Hello, everybody. So what we're going to do right now, I'm going to go through an example of a hypothesis test, and then at the end we're going to look at the pieces of it because there's these pieces that are going to repeat for every kind of test. Though we'll also I'll do another video afterwards with how these pieces change depending on certain details. It's going to be very, very, very similar to confidence intervals, not in terms of the process, but the things we're looking for, right? Remember with confidence intervals, we had a confidence interval on the mean when we know the standard deviation, when we don't, and then a proportion. We're going to have the same three ideas here. So let's start with this situation that I've put up here. We've got a truck company that says the average wage of the workers is $9.25 an hour with a standard deviation of $1.55. And suppose there's an employment agency that suspects this average is actually lower. Okay, so they're going to try to do a test to see if they want to argue that this is actually lower. So they're going to go gather some data and see if they can construct an argument and legitimately claim that they have good evidence that it is lower. Okay, so there's a few things that they're going to have to do. What they're going to do is we're going to test for a rare event. Right, so here's the idea. We're going to go, or this company is going to go out and take a random sample of workers and see what their average salary is. Right now, it's completely reasonable that if the average salary is truly, or wage is truly $9.25 an hour, they might go sample some people and get an average salary of only $9.08 or something, right? Because samples can be different than the population. In fact, they're almost always different from the population, right? If you take an exam in your class and you have the average score is 85% and you sample 5 people, their average might not be 85%. It doesn't mean the average of the whole class isn't 85%. However, it's very unlikely that a large sample has a mean very different, right? If I went out and sampled 100 people from this company and found their average to be only $5 an hour, that would make me pretty suspicious, because that's a lot of workers, if I took a random sample, to have such an extreme average different than what this claim is. And so if it's too crazy, if it's too rare, something so unexpected, we'll say, you know what the best explanation is? It's that the 925 is wrong, and that actually the average is lower. So we have to put a number on this idea of too crazy, this rare event. And so this part is a little bit arbitrary in the sense that there's not a number that anybody can say, this is the number that means something is too rare. And by the number, I mean the probability of something happening. How unlikely is something, right? Is something that happens only 1 out of 10 times too rare? Or is something that happens only 1 out of 100 times too rare? What is that number? Well, depending on what you're doing, you can choose different levels for this. For our purposes, this is going to be given, and that's a whole other set of understanding and process to determine what this level should be. So for this problem, I'm going to say our rare events are events with a probability less than 1%. In other words, if I find an average salary in my sample with the probability of finding that average less than 1%, given that the average is 925 of the whole population, I'm going to say, you know what, I think this is too rare, okay? Again, I could have chosen 5% here. I could have chosen 2% here. So this is not the magic number. It's just what I decided. And in all the videos, I'm going to make it, and in this course, like, you won't ever have to decide that. Maybe not, and certainly not on an exam or a quiz. There might be a project where you get to decide that, but even then, there'll only be a few choices. Okay, so here's what the employment agency goes out and does. Now that they've set their rare event threshold, they sample 81 workers, and they find with this sample that the sample mean salary is $8.95, right? So here we have a sample. The sample of these 81 workers has an average of $8.95, right? Lower than the $9.25, and now the question is, how low is it, right? So here's what we're going to do. So behind everything, remember there's some central limit theorem stuff happening, right? So we're not always going to pay attention to this, but I'm going to mention it here so we can understand what's going on. The idea is this. We have this, let's say Acme worker wage, let's say is our random variable. And assuming that the company is correct, it has an average of 925, a mean of 925, and a standard deviation of $1.55. Right? Well, by taking a sample, remember we've created a new distribution, the sample mean wage for sample size 81. And remember, according to the central limit theorem, this follows a normal distribution with the same mean and a standard deviation of $1.55 divided by the square root of 81. Right? That was our central limit theorem. You take the old standard deviation and divide it by the square root of the sample size. Okay? So I'm not going to, and when you watch people perform hypothesis tests, they usually don't write this part out, and that's fine, right? The next step is where we would usually jump to, but here's how we get to that next step. There's the central limit theorem is behind all of this. Keep in mind, in this whole test, we're assuming that this company is truthful. What we're about to do is say, if you're telling the truth, how rare is it to get a sample like this? Okay. So what we're going to do, we're going to compute a z-score for this, for x bar. Remember, the z-score is just x bar minus, so remember, x bar is one piece of data from capital X bar, this distribution. To compute a z-score, we take the data point minus the mean, and we divide by the standard deviation. The standard deviation in this case is the standard deviation of the population divided by the square root of the sample size. That's this thing here, right? So I'm just writing it in symbols down here. What this works out to for us is 895 minus 925 divided by 1.55 divided by the square root of 81, right? Remember, if you're doing this on a calculator, you have to, there's some order of operations stuff you have to be careful with here. So you might want to compute these in separate steps, or if you have a computer or a graphing calculator, type it in with the appropriate parentheses and all that. So this works out to be negative 1.74. Okay? So we're going to use this z-score here to test, to check if this event was less probable than our threshold, right? So let me draw a picture of what we're doing here. And there's two ways we can test this. Okay? So when I've converted to a z-score, I'm looking at the standard normal distribution, right, with a mean of 0 and a standard deviation of 1. Okay? So when we said this events with probability less than 1%, in other words, what I'm asking is it how, what do I want to say? How rare is it to get, what I want to test is how rare is it to get a sample of 895 or less, right? This or less. That's how we're going to think about this. We're going out to get samples, and we want to set the line where if we get a sample of some value or less, then we'll call it too rare. In terms of z-scores, right, here's how this cutoff works, this 1%. Since I'm looking about, I'm testing if the mean is less, I'm looking at the bottom end of my distribution. And so if this tail down here has 0.01 area in it, that's my cutoff. I can use an inverse normal calculator, right? We've done this before, and I find the following, that a z-score of negative 2.326 has a z-score, there's below that z-score, there's an area of 0.01. In other words, events with z-scores of this or lower, if we take this number and look below it, are going to have smaller probabilities than 0.01, right? However, our z-score is somewhere over here, negative 1.74. What that means is the probability of getting negative 1.74 is this red area plus this 0.01, meaning it has to be larger than 0.01. In other words, P of having z less than negative 1.74 is greater than 0.01, right? And I can just tell that from this picture. I have this critical z-score. Any z-score below it, right, if I put in a number smaller than negative 2.326 here, I'll get probabilities less than 0.01. That would be past our critical number, our rare event threshold, right? But in this case, I don't. It's on the other side. In fact, we can compute this probability exactly, negative 1.74. This probability using a probability calculator has a probability of 0.0409, okay? And so, because what this is saying is the probability of going, if, let me start this sentence over. If the Acme truck company's claim is true that their mean salary is $9.25 with a standard deviation of $1.55, then the probability of me going out, taking a sample of 81 workers and finding a average salary of $8.95, that has a probability of happening just over 4% of the time, 0.0409. And while that is unlikely, right, 4% is not a large probability, it's not unlikely enough for me to storm into that company and say, you guys are lying and your average salary is actually lower, right? I set a threshold. I said, if I don't come back with something less probable than 1 in 100, than 1%, I'm going to accept what they've said. In other words, we're not going to reject. We don't have evidence to reject Acme's claim. Now, I'm going to be clear, that's by our own standards. I could have chosen this 1% to be 5%. That's also a typical value for people to use, right? Then this critical z-score would have been somewhere over here, and we would have been on the other side of the line. The same test, same numbers. It was our decision to choose that particular value that put us on the other side of the line. Now, there are reasons we might choose that, right? You have to start thinking about what mistakes would mean, right? So for instance, if, let's say Acme is correct, but I think they're wrong, what's the consequence? Well, I make an accusation that's false, and you can decide how big of a consequence that is, right? Versus if you're doing this test on something like determining if a medicine is dangerous, the consequences are much worse, right? So there's always this little measure of what is the consequence of being wrong, and there's different ways we can be wrong. We'll talk about those later. So the last thing I want to do in this video, this is a complete hypothesis test now, right? This is the idea. Did we come up with an event that's so rare that we are willing to go in and say, we don't believe what you said, okay? But we didn't in this case, so we don't reject their claim. So let's go through the parts of this, because there are the pieces that we used here exist in every hypothesis test with details differing. So I just want to go through some of these pieces, okay? So each test is going to start with two things. We call them H0 and HA. Sometimes people call this H1 as well. H0 is, both of these are going to be statements about the thing that we're testing. In this case, it was a mean. In other cases, it'll be the proportion. right? So in both cases, it's going to be a statement about the mean or the proportion that we're testing. This one, H naught, we can think of as the status quo, right? The thing that's accepted to be true. So for instance, in this case, this was mu is equal to 925, right? And H naught is always going to include equals. It could be equals, less than or equals to, or greater than or equal to, but it's always going to include one of those. HA, or the alternative hypothesis, I should put these in here. Sorry, I forgot to write the name. This one is the null hypothesis and the alternative hypothesis. This is the claim that we are making, right? Or the thing that we believe to be true. This is our claim, right? So the Acme Chug Company has an average of 925, but we believe this is not actually the case, okay? And our claim, for instance, in this case, was that the mean was actually lower, right? We're not trying to claim what it is. We're just saying it's not what you say it is, right? And the claim is never going to include an equal sign. Claims will always be something like not equal to, less than, or greater than, okay? Right, so in this case, we're strictly less than, right? We'll do examples with all of these and how they differ, right? This determined, for instance, that I was looking to the left on this graph because I was testing below the mean. So I'm going to be testing for some critical value and below. Okay. Each of these will have a consequence like that. So we always start with these, right? The null hypothesis and the alternative hypothesis. All right. Then we're going to get what we call the level of significance, right? And this is, the symbol we use for this is alpha, right? This is our cutoff value. This is our, this was what we did right here. How unlikely does something have to be? So in our example, alpha was 0.01, okay? So each problem will have its own alpha. 0.01 is a typical one. We'll see 1, 2, and 5% pretty often. That's what alpha is, right? So it's just a name we're giving to alpha. So next, we compute what is called the test statistic, okay? This is always going to be, this will be a z-score or a t-score, right? So for us, this was our z-score of negative 1.74, right? This is this right here. And this here is the test statistic every time we're testing a mean when we know the standard deviation of the population, right? We'll use this. So again, I showed you this part in the brackets here is how we come to this test statistic, but we don't have to go through this each time. These hypothesis tests are done so often, we just get down to this sort of formulaic way of doing it. In general, the test statistic will depend on the distribution, meaning, are we using, do we have the one we have here? We're testing the mean, standard deviation is no, that has one, known, we have one test statistic. Are we testing the mean, the population standard deviation is unknown, then we use a t-score. And are we testing a population proportion, then we use a z-score, but we compute it differently than we compute it here, right? So remember with confidence intervals, when we computed the error, it was the same idea. We have a z-score or a t-score, and we compute the standard deviation in different ways to compute that error, right? But it was the same idea in both cases. We'll get the same thing here, okay? So we compute the test statistic. In our case, it was this z-score in the one we did. And then we make conclusions, okay? And let's say make, well, yeah, we'll just say make conclusions, right? So what that means is we look at our z-score and we check how it relates to the alpha, right? So there's two ways we can do this, right? We can compute the p-value is the probability of the testing event. Right? What I mean by this is, for instance, in the case over here, it was the probability of getting a salary of $895 or less. We tested that right here. We used the z-score to test it, but this probability represents the probability of getting our $895 or less, right? The or less part is always going to depend on how this is written. If we were using this one, it would be or more. If we were using not equal, we have to look in both directions. So there's a lot of detail in this that we'll cover in various examples, right? If you're using this p-value, you compare p-value to alpha. If the p-value is less than alpha, then we reject the null hypothesis, right? So if we had found a probability much lower, we would have said, you know what, this is so rare, I don't believe Acme Truck Company. I reject their claim that the mean is 925. Or, like in the case we just did, if the p-value is greater than alpha, then we fail to reject. Right? And the language we typically use is we reject or fail to reject with, in our case, for instance, a 1% level of significance. That tells somebody who's reading your work how strong your test was, right? So rejecting at a 1% is different than rejecting at a 5%, right? So this is a perfect example where this is rejected at a level of 1%. It's not rejected at a level of 1%. We fail to reject the null hypothesis. We would reject it if we were testing at a 5% level of significance, right? We'd have an opposite result, okay? But those are the two things that can happen with a p-value. Less than, I guess I typically do it greater than or equal to. The other way to test is to compare, so make conclusions. We can either do it this way. We can compare the test statistic to, let's call them the critical values. What I mean by this is the picture we did here. I knew from my picture that if I had a z-score less than negative 2.326, that the probability of being at that z-score or below was going to be less than 0.01. If I had a z-score higher than that, I know the probability is bigger. So I don't actually have to look at the actual value. I didn't really need to compute 0.409 if I had computed this negative 2.326 first. So I kind of did both in this example. You really only need to do one. And you check, you can create what's sometimes called a zone of rejection. Right, so it's hard to write down exactly how to define this because it depends on too many things. Depending on the direction of the alternative hypothesis, the zone of rejection can be, like in our case, below some value, above some value, or outside two values. So I'll do examples to get into the details of that. But basically, if your test statistic is in the zone of rejection, you reject the null hypothesis at that level of significance. And if it's outside the zone of rejection, you fail to reject, right? Notice we don't say we accept or support or anything like that. This test did not give evidence that their average was 925, right? We found a much lower average. We just didn't have enough evidence to claim that it couldn't be that we don't believe it, okay? It's sort of like a court of law, innocent until proven guilty, right? You don't get proven innocent, you just get not guilty. You're guilty, or we don't have enough evidence to say that you're guilty, right? That's kind of the world we're living in here. Okay, that is gonna be it for this video. What we'll see in the next few is that we're gonna streamline this. I'm gonna go through the three kinds of hypothesis tests we can do and where the details differ are, but they're all going to have the same set of steps. Create your hypotheses, decide the level of significance, though typically that will be given to us, compute the test statistic, and then use that test statistic to make conclusions. And we'll work on both ways of doing this The reason being, not only is this the point of this to learn how to do these things, the point of this is to learn how to understand when other people do them, and other people might choose to do one or two of either of these methods, and you want to be able to understand their work. If you're reading a paper that's relevant to your job, you want to understand the meaning of that paper. Okay, that's really it now. Thanks, everybody. I will see you in the next one.